Hi everyone, welcome to building a trusted language extension for Postgres. My name is Jonathan Katz. I'm a principal product manager on the Amazon RDS open source team. And today we're going to explore how you can build your own extensions using your preferred programming languages and install them directly on Amazon Aurora and Amazon RDS. So before we get into that, first let's learn a little bit more about Amazon RDS. Amazon RDS, or Amazon Relational Database Service, provides your choice of preferred databases for you to run your workloads. These include popular open source and commercial engines, as well as Amazon Aurora, which is Amazon's own commercial built database for supporting workloads of any scale and size. It- what Amazon RDS provides is the ability for you to easily administrate your databases, so you don't need to worry about backups, OS patching, taking in security fixes, and also focuses on keeping your workloads up and running. They're available and durable with automatic multi-AZ options and features like Amazon Aurora Global Database that let you manage your workloads across multiple regions. Amazon RDS is performant and scalable. It's very easy to scale up storage and scale up compute with a few clicks. And it's designed to be secure and compliant with the ability to encrypt your databases using Amazon KMS and be able to encrypt data in transit and at rest. So just highlighting this, a few more things on what it means to be fully managed. This is the idea of shared responsibility, where AWS is focused on managing all of the operations around your data, so that way you can focus on building out your business logic. Take schema design. By trade, I'm an application developer, and really all I want to focus on was building out my schema, writing my queries, and I didn't really want to have to worry about managing a database. So this is what Amazon RDS takes care of for you. With dealing with automated failover, backups, monitoring, all the tools that are needed to keep your data available and running, so you can focus on what you do best, which is building out your application. And in some ways that gets into our subject for today, which is building extensions into Postgres. Before we dive into that and what an extension is, first, let's understand a little bit why people are running Postgres. For one, it's open source. There's been an active developer community around it for more than 35 years, about 25 of which Postgres has been open source, actually a little bit more than 25. Postgres is not controlled by a single company. It is truly free and open source. There's a whole variety of organizations out there helping to support Postgres, as well as many individual developers. I've actually been a part of the Postgres project for over a decade now. I'm a member of the core team, and I've been focused on a variety of the governance issues related to Postgres. Beyond Postgres being open source, what people also like is the fact that it is there for performance and scale. Postgres has robust data type implementations. Beyond just integers and characters, there's supports for dates and times, ranges, polygons, JSON, and by supporting a robust set of data types, it makes it much easier for developers to build their applications. I used to have to manage a scheduling application, and the date and time types and the range types made it so much easier to write queries to check when a room was available or what dates were not available to book up that room. But it's one thing to be able to store the data. You also need to be able to get it out of the database, and this is where Postgres indexing support has won a lot of fans. In addition to the standard B-tree indexes you find in databases, Postgres supports some advanced types for introspecting those more complex data types, such as JSON or dates and or date ranges. Those include like the gist index, the gin index. In fact, the gin index is actually used for full text searching. And when I was managing that scheduling application, gist indexes were very important for me to quickly query against date ranges and see what was available. There's also features for being able to support larger workloads as well, including parallel queries, being able to use multiple workers to parallelize and speed up the process of retrieving a lot of data, as well as support for partitioning natively and federating data out to multiple Postgres databases. But one thing that makes Postgres a lot of fun to work with is the ability to extend Postgres and add more functionality without having to fork the database. Now, this is a very powerful concept, and this is captured in something called a Postgres extension. So what is a Postgres extension? I mean, really what it is it's its own software package. It can have its own independent software lifecycle, but it adds additional functionality into Postgres. And that's really powerful because if I'm able to bring more functionality into my database without having to fork it, it makes it much easier to build applications, support what workloads I need to support within Postgres. There's actually a very large landscape of Postgres extensions. In fact, I'm not even sure how many there are. I know that there's a list of at least 1,000 that are out there, and these extensions are both open source and commercially licensed, depending on the person who or people who are working on that extension. Within Amazon Aurora and Amazon RDS, there are currently over 85 Postgres extensions supported. And what's great about this is that suddenly, by using these extensions, you can get additional functionality in your Postgres databases without having to fork the database. And in many cases, if the extension's already there, you can just call, create extension, and it's available. You don't need to do a restart. So a little bit more on Postgres extensions. Postgres itself was actually designed to be extensible from the get-go. This is the idea of a object relational database. And Postgres did add a formal extension framework in the 9.1 release in 2011. So the modern syntax for managing Postgres extensions has been around for a while. But as mentioned, Postgres extensions predated that. Many of them were stored in the Postgres database as something called a contrib module. Most databases are already using one or more extension, and we're going to cover a few of these extensions here to see if they resonate with what you're already doing with your Postgres workloads, or maybe inspire you to add these extensions into your workloads, or maybe create your own, which will be the subject of what we're talking about a little bit later in this workshop. So probably the most popular extension in use is pgstat statements. If you're using any monitoring software, an application monitor, or anything that's really trying to pull data out of Postgres to understand what's happening with your queries, you're probably using pgstat statements. Effectively, what pgstat statements does is that it tracks the performance of every query that's running within your Postgres database. And it is like the go-to extension for troubleshooting query performance. pgstat statements has received a lot of improvements through the years, and can be used to help identify where the bottlenecks are in your application vis-a-vis what you're doing with your database. It's also pgpartman. As I mentioned earlier, Postgres does support native partitioning, but you might need some additional help in managing the partitions. For example, if you have data that's time series related, you want to be able to automatically create partitions as you need more data or need to archive data, and pgpartman can help with that. It can also help optimize your data access patterns, particularly around larger tables, because it's providing that layer of partition management on top of Postgres's native support. Once upon a time, before Postgres had that native support, I did have to manage data around TV schedules, and it was a clear need for something like a pgpartman. pgpartman did not exist at the time, but had it existed, I definitely would have used it to manage my data. Now, Postgres has a framework within it to be able to talk to other databases. This is called foreign data wrappers, which is part of the SQL Med standard. And the idea with the foreign data wrapper interface is that you can talk to other data sources. The most popular one is the Postgres foreign data wrapper, which lets a Postgres database talk to other Postgres databases. So, this can be used for data federation, sharding, etc. But Postgres supports a wide variety of foreign data wrappers that can talk to other databases as well, such as MySQL and Oracle, to name two of them. What's also nice about the Postgres foreign data wrapper is that it works with Postgres compatible databases, such as Amazon Redshift. So you're able to query directly into these databases and extract the data with them, put data into them, etc. And last but not least on our tour of some of the existing extensions, there's PostGIS, which is probably one of the most robust Postgres extensions out there. This introduces new data types and functionality that's geared specifically towards geographic data. Now, one way to look at it is that if you're using a map somewhere on the internet, you're likely using PostGIS on the back end. OpenStreetMap, for example, uses PostGIS. What's cool is there's even, if you look at all the Postgres extensions out there, people actually build extensions on top of Postgres extensions. So PG routing is a Postgres extension that provides routing information. So how do you get from point A to point B, and algorithms around that. but depends on PostGIS. So you can see what's happening here with all the software packages available out in the Postgres extension ecosystem is that you ultimately can build up some very complex functionality and package them in these extensions, and depend on functionality that exists in other Postgres extensions. So Postgres extensions are really cool. Like we've seen, even just from these examples, how much functionality we can add into a Postgres database, and not have to do any additional work on the core database software. But there are some challenges that we need to keep in mind as we look into extensions. So for example, installing extensions requires access to a file system. And this is probably something that, as a database administrator, you might not want to give out to your end users. You might want to act as the gatekeeper for extensions that are installed, but typically you're not giving direct file system access to your database system. Managed service providers and running databases in systems like containers also have restricted file systems. So people are not necessarily giving out the access to install new extensions there. Likewise, an extension may not be universally available. That perhaps like one system where your Postgres is installed, has an extension available, but another doesn't. So that could make it harder to shift data between these systems, particularly if you can't fully migrate the schema because an extension is not available. Upgrades can also be challenging across Postgres major versions. A lot of Postgres extensions are written in C. This is due for performance reasons. Postgres itself is written in C, and being able to perform at the same level as Postgres, it helps to write the extension in C to be able to maximize performance. But also from an interface standpoint, a lot of the functionality that Postgres extensions use rely on being able to make calls directly to Postgres functions that are also written in C. So you need to be able to write your extensions in C in order to be able to access that. So for an example, the foreign data wrapper interface is implemented in C. And while it might be possible, well, it is possible to abstract that to another language, it's more convenient to be able to use the functions that are already available in C and be able to write your extension in C. However, the Postgres code base can change between major versions where function definitions change, and then this would ultimately break the extension code that you wrote unless you put in the appropriate C code to be able to manage this. So extensions are pretty cool. Like we can add functionality, we can make it much easier for us building out our applications to be able to use Postgres, but there are some of these challenges in using them. So what can we do to make it easier to build Postgres extensions and be able to avoid some of the challenges that make them harder to adopt? This is where trusted language extensions comes in. So trusted language extensions helps to solve some of these challenges. Trusted language extensions is an open source Postgres project that does a few things. First, it provides a SQL-based interface for being able to install and manage extensions without having access to the Postgres file system. It also abstracts away a lot of the C functionality that's required to build Postgres extensions and exposes it in a way that's safe for developers to be able to build extensions that normally would require C code. Trusted language extensions, provides also a security layer in order for a database administrator to choose who can install trusted language extensions. So that way, there is a gatekeeper in order to add this new functionality. But a lot of the crux of trusted language extensions, or TLE for short, is using something in Postgres called a trusted language. A trusted language in Postgres is a programming language that has certain security properties, so that way an unprivileged user can write procedural code and not be able to violate the security boundary. So a trusted language by definition is not able to access the underlying file system in Postgres. It also is not able to escalate privileges beyond what the user already has. So that way it's creating a barrier so that users can safely write their application logic, but not worry about creating any security issues. So if we take the trusted languages that Postgres already has and combine it with TLE, we're able to let developers write their own extensions with appropriate safeguards put in by your DBA, and be able to use parts of Postgres that they normally were not able to use before, and finally be able to install Postgres extensions into any file system, or sorry, into any Postgres database that supports trusted language extensions. So, for example, Amazon Aurora and Amazon RDS don't provide direct access to the file system, but do already support over 85 Postgres extensions. Now, with trusted language extensions, you can write your own extensions and bring them to Amazon Aurora and Amazon RDS and be able to manage their own lifecycle independently. So let's look a little bit more into this. What does TLE provide? So first, there's improved safety. Trusted languages do have the security guarantees that we talked about, but there's also some crash safety guarantees as well, based upon how these languages are constructed. With C, C is a very powerful language, but it's, if you're not careful, you can write some unsafe code with C that can either, crash your database system or, inadvertently create a security vulnerability. Trusted language extensions takes this away because by using a trusted language, you're able to write code, but have the security guarantees that come with that trusted language. This also allows TLE to expose safe access to Postgres internals. So you can start writing things, for example, using a Postgres hook, which we'll cover in a few slides, and be able to appropriately code that in. Healing languages can also provide the performance that you need in order to solve your business challenges. That, as we add more trusted languages to Amazon Aurora and Amazon RDS, you can get near C-like performance and be able to, solve the challenges that you have and not worry about, performance slowdowns. And there's flexibility that you can manage the software lifecycle for your extensions and your business logic. This is a very powerful concept, and something that I used to have to deal with quite a bit, where I was writing stored procedures for a search algorithm, and this algorithm would change from time to time, but it was really difficult for me to manage and package it. And even though I did use some database migration software, the package of my search algorithm was almost like all over the place. Like, sure, it was like in the database in one spot, but it would be hard to introspect and know exactly what version of that was running, particularly if I had to install the search algorithm on multiple database instances. With something like trusted language extensions, I'm able to package that software and version it similar or just like a Postgres extension. So I'll always know exactly what version of the software is running at any given point. So let's look at this in terms of how it works and what your software development cycle would look like. First, you have a customer problem you need to solve, and it makes sense to do this with a trusted language extension. Say, let's take the search algorithm example. I need to build a search algorithm to look for available spaces. So first, I'm going to build this, and I'm going to build the stored procedures that I need to do using one of the trusted languages that are available today. In Amazon RDS and Amazon Aurora, those languages are JavaScript, Perl, Tcl, and Postgres is PL pgSQL. Once I build out that extension, I can install it. I can install it using the API that TLE provides, and again, it's all SQL based. So, so long as I have permissions to install it from my DBA, I can install that extension. Once that code is on there, it behaves just like any other Postgres extension. You can call create extension, drop extension, etc., and that extension gets created. So I've built my search algorithm. I've installed it into my database, and I've now created my extension, and I send the search algorithm off. I let my users use it, and then much like any other piece of software, you collect feedback, you learn how your users are using the extension, and you can ultimately iterate on it. And I can create an update to my search algorithm, and just like any other Postgres extension, I create the appropriate update language. I can then install it, run alter extension update, and then there's the newer version of the search algorithm. So trusted language extensions lets you build out a virtuous cycle for being able to continuously update your code and have it run well in your database. So how do I get started with this in Amazon Aurora and Amazon RDS? So first off, there's a special shared preload library that you do need to load in. It's called pg_tle, and you can do this from adding it to a DB parameter group. So once you run either from the command line or the console or CloudFormation, once you put in your DB parameter group, you put in the name, you add in pgtle. It does require a restart because it is a shared preload library. But once that's set up, all you have to do to enable TLE is run create extension pgTLE. On Amazon RDS and Amazon Aurora, you will need to grant a special role called pgTLE_admin to any user that you want to be able to install a pgTLE extension. We'll see that in the demo in a few slides. So how do you enable trusted language extensions in your Amazon Aurora and Amazon RDS databases? You will need to enable a parameter group, specifically a parameter called share preload libraries, to enable pgTLE. The pgTLE shared library provides the interface between your SQL and the Postgres internals. So once you've added that to the share preload libraries, it does require a restart. But once it's installed, all you have to do to load pgTLE is run create extension pgTLE. On Amazon Aurora and Amazon RDS, you will need to grant a special role called pgTLE admin to any user that you want to be able to install a trusted language extension. So it's up to you as as a database administrator to decide who you want to be able to have access to that extension. All right, so how do we manage the TLE once we've enabled it? This can be done through the pgTLE install extension function. The pgTLE install extension function is the magic that lets you bring your code into your Postgres database and have it managed like any other extension. The first thing you need to do is you need to name the extension. And this is done through the first parameter called TLE. In this case, we're calling it TLE test. Then you need to give it a version. And this is great because now you're actually versioning your stored procedures within Postgres using TLE. Then there's the body of the extension. And this is where you put in all the logic you want for your code in order to manage it through TLE. In this case, we're just creating two functions, one called re, the other called invent, that return a couple of values. But this is what's ultimately getting installed into your Postgres database. And if you want to enable it within your database, all you have to do is call create extension TLE test. And it's just like any other Postgres extension at that point. The functions are installed into your database and you can start using them right there. Now, let's say you want to update the functions. In the previous example, we were returning 1 and 2, but now we want to call 10 and 20. Well, TLE follows, as I mentioned, the software development lifecycle, and it follows it within Postgres. So what you do in this case, if you want to update from version 0.1 to 0.2, you need to install what's called an update path, and you'll provide the appropriate code to do so. So if you see in this example, what we have here is that we're saying that this is the way you upgrade from 0.1 to 0.2, and here are the new functions that we're going to add to replace the existing ones. Note that in this case, we're using create or replace function because these functions already exist within the Postgres database. We want to indicate that we want to overwrite the functions with this new code. Once this is installed, all you have to do is run alter extension TLE test update to 0.2. There's an additional TLE function that allows you to set the default version of an extension, which is the version that would be installed if you would call create extension TLE test, or if you run alter extension TLE test update and not specify the version. Now, we've covered the fundamentals around being able to install and manage trusted language extension. So let's look about how we can interface with some Postgres internals to build some even more powerful extensions. And first, we need to understand the notion of something called a hook in Postgres. So what is a hook? When you send a query into Postgres, it goes through a process in order to be able to ultimately execute and get out that data. So the first things first is you need to be able to parse the query. So once you parse the query, it goes to something called the TCOP or the traffic cop, which basically determines if this is a read or a write or a utility command, something that's doing some level of DDL. So once it's done, once it's done going through that process, it goes through the rewriter, which translates the query into something that Postgres understands and sends it to the optimizer. And the optimizers could determine the best way to be able to fetch the data or write the data to Postgres based upon what it understands about the statistics of the system. And once it's built out that plan, it goes to the executor to actually get that data out. Now, where hooks come in is that Hooks can let you alter the execution path and be able to add additional functionality, or in some cases, completely rewrite the functionality of what's going on in Postgres. So what do I mean by that? Um, so a basic example I would take is something called a check password hook, where if you're authenticating into Postgres, so a basic example of a hook is a check password hook. Let's say I want to change the password on my user account, but I also want to make sure that I'm enforcing specific password rules, so I'm not setting a weak password. Postgres provides something called a check password hook that lets you set your own password rules that make sense, that are in line with what your organization wants. So that way, Postgres is not dictating how those rules are set. You can determine how those rules are set. And if I'm trying to set a weak password, I can ultimately have Postgres reject that. A more complex example of a hook is something called a process utility hook that lets you look at the query that's been parsed and ultimately change the behavior of that based upon your organizational needs. So for example, if let's say I want to explicitly block all DDL commands on a Postgres system during a particular state when I set a configuration parameter, I can do that with a process utility hook where I can capture anything that looks like a DDL command and then choose to ignore it or reject it and send it back to the user and say, hey, I'm not going to execute that right now. So hooks are very powerful, and they're able to plug into all different parts of the Postgres system. Currently, there's a total of 30 hooks in Postgres 15. And what's great is that a lot of the extensions already out there for Postgres do utilize hooks to build out all sorts of functionality. Now, trusted language extensions also allow you to enable hooks. And currently in TLE, we support this enable password check hook that I was describing. In order to enable the hook, though, there's a configuration parameter that you need to set because you may not necessarily want to enable a password check hook at any given time. Specifically for the password check hook, there's three values you can set. You can disable it, with the parameter value for that is off. You can turn it on for any database that has the password check hook installed, or you can require that the password check hook executes across all databases. But keep in mind that if you're going to set that to be required, you do need to make sure that your password hook function is installed in all databases. Now, so what do I mean by a password hook function? We need to be able to tell Postgres how to execute the logic for our check password hook, according to our own rules, and this is going to be captured in a custom function. So we need to be able to register that function with TLE, so that way TLE can put that into the check password hook. So whenever a user requests changing a password within Postgres, we know which check password hook functions to execute. So we're able to do this through something called the TLE Feature Framework. And what the TLE Feature Framework does is that it binds your stored procedures written in trusted languages to the Postgres internals that are exposed by TLE. What's cool is that you can actually assign multiple functions to the same TLE feature. So you can have multiple check password hook functions assigned to the check password feature. You can register and unregister them as needed. Basically, it's a way to give you maximum flexibility for how you define your trusted language extension features. So how do you create a hook function? You basically write it like any other Postgres function and then ultimately register it to the TLE features. We're going to look at this in an example, in a few slides, and we're going to actually build out our own check password hook function. The one thing to keep in mind though as you build out hook functions is that you do need to match the function signature for what the hook function looks like. Otherwise, it won't be executed. So there's some things to keep in mind with security around hooks, that a lot of these hook functions do execute with elevated privileges. So you don't necessarily want to have every user in your system writing their own hook functions. You need to have this special role, pgTLE admin, in order to actually register a hook function. So there is some shared responsibility here where when you're building out these hook functions, you do want to audit them and make sure that they're in compliance with your security requirements and they're not doing anything fishy. And you also want to make sure that you're only giving out the pgTLE admin role to users that you trust. Now, we've talked about trusted languages, but we haven't, gone in depth in terms of how you choose a trusted language. And one of the biggest things when selecting a trusted language is familiarity. You're most comfortable in the language you're most comfortable with programming it. It's a tautology, but it's true. And as you're looking through this, while you might think one language has particular features you're more interested in, or it might just be fun to write in, languages do have their own technical advantages, but you should err on the side of familiarity when first making this decision. In terms of available trusted languages in Amazon Aurora and Amazon RDS, today there's support for pgSQL, which is Postgres built-in language, PLV8, which is JavaScript, PL-Perl, and PL-Tickle. And we're looking at adding even more trusted languages in the future. Now, PL-PGSQL is the most built out in terms of accessing a lot of higher level Postgres functionality. So when in doubt, we do recommend using PL-PGSQL, but you do have a choice to choose what language you're most comfortable with. Diving a little bit deeper into what PL-PGSQL does, first off, it's installed by default on all Postgres databases, so it's fairly universally available, and it's very easy to make calls to the database, select calls, insert statements, etc. So this is why, one of the other reasons why we generally recommend that when in doubt, use PL-PGSQL, because it's going to give you the most functionality to work with Postgres out of the box of the trusted languages. It's frequently used when doing Oracle to Postgres migrations. There's similarities to PL/SQL, so that way, people with an Oracle background, feel comfortable working with PL/PGSQL. Now, yeah, I used to, work a lot in the web world. So, I picked up some JavaScript, and PLV8, is a way to be able to write JavaScript code directly within Postgres. If you're working a lot with JSON data, JavaScript has excellent JSON support, so it makes it, much easier to manipulate those objects. What's also cool about PLV8 is that it works very well with other user-defined functions that are that are also defined in PLV8, that you can call them directly without having to go through the full Postgres function calling engine, which has some advantages if you are working so exclusively within PLV8. Now, we spent a lot of time setting everything up today. I think the best thing to do is make this less abstract and work on a demo. I mean, I know personally, I work best, when I see the code. So let's switch over to the demo. So today we're going to build two trusted language extension functions. The first is going to be a series of distance functions that let us calculate distance in a few different kinds of ways. And the second is going to be a check password hook function that enforces certain password rules, namely not having a password that's in a common password dictionary. We're actually going to write these functions in JavaScript just to show how you can use trusted language extensions with PLV8. So our first example, we'll just walk through it real quick before we go to the command line. We're installing an extension that's going to create two distance functions, one for the Manhattan distance, the other for the Euclidean distance. That has a common distance function ancestor, but we're going to install it and be able to enable it in our database. So just to recap, Euclidean distance is the direct line of sight distance between 2 points. So, this would be Euclidean distance. The Manhattan distance, also called the taxi cab distance, is the distance between, you're going indirectly around objects, kind of like walking around in Manhattan. I live in Manhattan, so it's it's a very common thing to count things in blocks. All right, so let's now go to our command line. Now, first we need to make sure that TLE is installed in our database. So we're going to do that. And let's make sure that we've already enabled the different command line options we need today. So it looks like pgTLE is in our shared preload libraries. Well, it would be, because if it isn't, the command create extension pgTLE would not work. We're also going to see if our password check extension is enabled. It is. So we haven't installed anything yet, but we just want to make sure that's enabled. Now, I need to grant the pgTLE admin user to my current user. That way I'm able to install the extension. So let's go back and we're going to install that extension code. All right, so this looks like it's installed. There's a function called pgTLE available extensions that will show us what extensions we have available. So we can see that we've installed this extension called pgDistance. So let's install it. Or we've already installed, let's create the extension. There it is. We've created the extension. We can see that we've installed several distance functions now into our schema. So let's calculate the distance. Let's see what the Manhattan distance is between 2 points. Okay, seems to work. How about the Euclidean distance? Right, it seems to work. So we've shown that the straightest point, the closest, it seems to work. So we've shown that the shortest distance is through, not around. All right, so we've been able to install this. So let's try to drop the extension and see what happens. So we dropped it. See, these functions no longer exist. And let's see if the extension is still available, but let's see what happens if we try to uninstall the extension. All right, so this returns that we've uninstalled the extension. And if we call available extensions, we can see it's no longer there. So cool, we just managed the full life cycle of this PG distance extension. And notice how easy it was to do this from the TLE SQL interface. All right, so let's do a little bit more of a more complex extension. Now we're going to install an extension that enables a check password hook, and it's going to look up passwords against a bad password dictionary. So again, we're going to write this in PLV8 or JavaScript just because, having a web background, I'm a little bit more comfortable writing in JavaScript. But again, you can write this in any of the trusted languages available on Amazon RDS and Amazon Aurora. So what are we doing in this extension? So we're setting up a special schema that's just going to contain the password check hook function and our bad password dictionary. And we're going to restrict access in terms of who can actually edit it. We don't want unprivileged users to be able to modify the bad password dictionary or modify the hook function because they're using this to enforce good password practices. So after we set up those rules, we create a dictionary. Here are 10 of the most commonly used passwords. And then we're going to define the check password hook. And we put in a few different types of ways of checking for the passwords in here. So if it's a plain text password, we're able to compare that password directly against the check password dictionary that's there. And that's what this case is. If the password's in the MD5 format, we had to do a little bit more work to be able to make that comparison, but we were able to do that from this SQL call. And again, we put in some error logging and warnings around the specific behavior. And then once it's complete, we're going to grant the appropriate execution permission on this function. So we want all users to be able to execute it. And then from within the extension installation code, we're going to register this check password hook, as part of the check password hook we want to write. We're able to do this from within the extension code because when we uninstall the extension, or sorry, when we drop the extension, we actually are able to unregister the feature automatically. So let's now install this and see what happens. All right, we've installed the extension. Now let's find it in our list of available extensions. We'll create the extension. Great. So keep in mind, we've already enabled this, the ability to do a password check. So let's try it out. Let's try to create a new user with one of the passwords that's in the bad password list. And I know password is in there. So look at that. We got an error. And it says, password must not be found in a common password dictionary. So the enforcement is working. Now let's try to be a little bit sneakier and create a password using the MD5 method. Now let's see what happens if we try to create, do the same exact thing, but send a pre-hash password in the MD5 format. So first I'm going to set my password my password encryption to MD5. And I'm going to do the \password psql command because this is going to pre-hash the MD5 password. So I'm going to type in password. Please trust me since you can't see it. And we see that what I just typed in was found in the common password dictionary. And this was doing the MD5 check. So finally, let's see if can I actually create a password that's valid. We'll do it in plain text so we can observe this example. So yeah, here's a bunch of random stuff, and that works. So we can see that the password hook is doing its enforcement checks, correctly based upon the rules that we defined. Now, if I were to drop this extension, we've actually dropped the ability to do the password check. So if I try to create a role with a bad password, it's going to go through because we've removed the check password hook. Let me re-enable it just for a moment, so that way we can see where it was registered. As mentioned, there's something called the feature registration table. So I mentioned that was something called the feature registration table, which is where TLE knows to load in all the hook functions for the different Postgres hooks. So we can see that the password check hook we created is in this table. When I drop the extension, you can see that's unregistered, so that way Postgres is not going to fire those hooks. So what did we just see? We saw how we can install a simple set of user-defined functions as part of a trusted language extension. And we saw how we can create a check password hook to be able to enforce password privileges. So let's wrap this up to learn a little bit more about TLE, its future direction, and how you can help contribute to TLE. There's already extensions for Postgres that are trusted language extensions to date. They may be using the existing Postgres file-based format, but you're able to load them into any system that's using trusted language extensions. These are extensions written in pgSQL or other trusted languages. There's a tool available within the trusted language extension GitHub repository that lets you load these extensions. pgTLE managed local extensions that simplifies the process of being able to load it in. I mean, it really is from GitHub to RDS in less than a minute because you can just run this script, point it at an extension, and it will be automatically installed into Amazon RDS. For more documentation on trusted language extensions and how they work, please visit the Amazon Aurora and Amazon RDS docs, as well as there's an AWS news post that announced the launch of trusted language extensions and runs through some examples. Last but not least, TLE is an open source project. It's released under the Apache 2.0 license, and you can get it on GitHub at the AWS/PG_TLE repo. We'd love to hear your feedback on it. We love contributions as well. We hope that pgTLE is very helpful, and we believe that by having it be open source, we can not only make TLE better, we can continue to add more features, get your feedback, and iterate on it rapidly, and be able to help you make it easier to run Postgres extensions on any Postgres system. So pgTLE can work anywhere that you run Postgres, and please try it out and give us feedback on it. So thank you for joining us for the webinar today, and I'm happy to answer any more questions that you may have.